Welcome and thank you for joining. I'm Nigel, a PhD student at the University of Massachusetts Amherst, advised by Professor Andrew Lan. I'm going to present our work on using pre-trained language models for automated scoring of open-ended student responses for reading comprehension questions. The US Department of Education runs the National Assessment of Educational Progress, or NAEP, in various fields, including math, science, and reading. Every 2 years, millions of student responses need to be graded. The department hosted a challenge inviting AI models to automatically score student responses for reading comprehension questions. We are happy to be a grand prize winner of the challenge. This was a joint effort by the UMass RISE team. Automated scoring refers to the problem of using algorithms to automatically score student responses to open-ended items. This reduces human effort and scales well to an ever-increasing student population. Let's get to our NAEP challenge. We are provided with 20 reading comprehension items across grades 8 and 4. Each item is associated with a long passage, a short question, and a data set of around 18,000 short to medium length student responses scored by human graders. This is an example of a reading comprehension item from grade 8, asking to describe what kind of person the merchant was in the story. Like this, we have 20 such items. A key observation in the challenge is that passages and questions are shared across items. Existing methods for automated scoring use pre-trained language models like BERT. These models are fine-tuned on student responses and are also combined with human-engineered features. But what are the drawbacks? Each of the 20 reading comprehension items would require a separate BERT model. We therefore would have to train 20 different BERT models, one for each data set, which is not scalable. Further, remember I mentioned about passages and questions being shared across items. Separate BERT models fail to leverage this item linkage and shared semantics. Before we explain our model, I'll introduce in-context learning. Large language models can be used to perform new tasks in a few short manner by using few labeled examples called in-context examples. Here, GPT-3 performs machine translation by seeing in-context examples in the input and tries to find the French translation of cheese. Coming back to our challenge, what's our key idea? We learn a single shared model across all 20 items using in-context learning. Since we train a single model for multiple items, these in-context examples help contextualize the model to each item. I'll break our model design and input structure into parts. On the left, we have 20 reading comprehension items, each with its own data set. Index I denotes the ith item and thus runs from 1 to 20. Each item has a passage and a question, seen here denoted as PI and QI. Index J denotes the jth student response in an item's dataset. We use the term meta-train to refer to a training style of learning a single shared model on the union of 20 datasets. We have 4 carefully designed input templates for the answer, passage, question, and the in-context examples. Let's focus on the answer template, which provides the student response text, the most important feature. We provide helpful task instructions like score this answer, which explain each input component and provides problem context. We also explicitly list the valid score classes in the input. Here, the numeric scores 1 to 4 are converted to poor, fair, good, and excellent. We use a similar style for the passage template and the question template. Finally, the in-context examples. When fine-tuning on a student response from the ith item, we append in-context examples, which are simply labeled student responses from the same ith items dataset. Since we train a single shared model across 20 items, these examples help the model contextualize to each of the 20 items. We use a shared classification head across all 20 items. Each item has a different score range, with the minimum being 4 and the maximum being 4. Dependent on which item the student response belongs to, we mask out invalid scores. Moving on to our experimental results. We perform a 5-fold cross-validation and report the average quadratic weighted kappa across all 20 items. As seen, machine learning methods perform modestly, demonstrating the difficulty of the task. Pre-trained language models beat machine learning models handsomely. Our proposed method performs best, approaching human performance. We make 2 surprising observations. First, that feature engineering methods perform poorly. Second, that adding passage and question text doesn't improve performance. Coming back to our key observation that passages and questions are shared across items, these results averaged across shared versus non-shared items from grade 4 and grade 8 validate our hypothesis of leveraging the shared information by training a single model. Our method performs much better than baselines on items which share passages and questions than non-shared items. We performed a qualitative error analysis by randomly sampling 100 student responses for the item asking to describe what kind of person the merchant is. The 5 main types of errors were: first, our model fails to understand responses with spelling mistakes. Second, there are scoring mistakes by human graders. Third, our model performs poorly on correct student responses using different arguments than those seen during training. For example, most answers scored highly by human graders describe the merchant as honest. However, describing the merchant as brave is also correct, which our model fails to understand. Fourth, incorrect responses with imitative syntax to correct responses confuses the model. Fifth, when there are multiple characters in the passage, our model at times confuses characters in the student responses. We make the following observations for future work. First, we need better ways to use the passage text. Our model is learning the task of score assignment to student responses rather than solving the reading comprehension task. Second, using spell-checked student responses improves performance. Pre-training BERT on student-written text could improve performance. Third, our model remains a black box and fails to provide explanations on why a student response was given a particular score. Fourth, although we perform fairness studies detailed in the paper, we can further explicitly control for fairness by using a training objective which promotes fairness across students. We make our code publicly available. Thank you for listening.